take any questions after class today. All right. I know the biggest question is what is up with exam two? There's something I have to double check before I release scores, and it's going to run me into late tonight and until probably early tomorrow. But during office hours, I should be available, or I should have all grades up. If you took a paper copy, though, you're more than welcome to come by my office to take a look at your version. Now, the score that you see on the paper version is probably going to change, but for the most part, you can see what you got right or wrong. Just today, if you don't mind, if you can shoot me an email before you come by. I just have another course that's trying to finish up a lab project. So they started early this morning and they're going to be in and out most of the day. So I'm probably going to be in and out of my office just trying to make sure that I'm accessible to them. But if you shoot me an email, I'll try to make sure that I can get you an opportunity to take a look at your test. Okay, so let's move forward with today's lecture because we want to finish off chapter 7 today, and then on Friday's lecture, I'll be able to just review some things. I do want to talk about how you guys are doing with mechanisms and all that, but I need some time to prepare some slides to kind of cover that. So we'll talk about that on Friday. But I'm going to try today to highlight some things that I'm seeing which could be problematic for exams. You don't want to make that same mistake when you guys are showing mechanisms there. Okay, so the big important thing about chapter 7 at this point is Zeta's rule. And what is Zeta's rule? Zeta's rule says that when I perform an elimination, I'm going to have a tendency to form the most stable alkene, all right? That's typically what you're going to see in solution from elimination processes. So what does that mean to us as chemistry students? Is that I need to recognize how to draw the major product. And if I look at this example here, right, there's an alpha group on the right side. There was just a methyl group on the left side. So this left on the opposite carbon or the neighboring carbon to the bromine here, a carbon that had 3 H's. And on the right-hand side, this carbon only had 2 hydrogens, right? So I had all these potential hydrogens that could eliminate. Which one do I choose? So if I choose an H from the side that had 3 potential hydrogens attached, I generate this alkene here, right? So the double bond is between this carbon that had the leaving group or the halide and that carbon that I took away or I removed the proton. So I have my double bond here. And if I investigate that alkene, this is a mono-substituted alkene, right? Okay. If I took a hydrogen from the opposite side that had 2 hydrogens, all right, this leads to a double bond here. So I hope you guys can see it here. Let's zoom in a little bit.
Dr. Cooper, I can't see your screen.
Okay. I'm going to stop the sharing, and then I'm going to reshare screen again. Okay, I think it should be sharing at this point. I'll take a show of hands. Can you guys now see the screen? So yes, no? Okay, I got one hand raised. All right, if you cannot see the screen, can you speak now?
I cannot.
Okay. No, I'm not too sure. I'm actually in the classroom today. I didn't think this would be that big of a difference. All right, I'm gonna stop the sharing one more time. And for those that can't see, I know it's gonna be tough. I might ask you guys to try to rejoin the class, but I do have the record.
Yeah, I was going to say, I can see yours, Doc.
Say that again?
I can see it.
Oh, you can see it. Okay.
Yeah.
I'm gonna have the recording on, so if you guys are missing anything, hopefully you can pick it up from the recording. Okay, somebody send me a message from the. Okay. All right, I just reshared. Can you guys now see the screen?
Yes, sir.
Okay. Is there anyone that cannot see the screen currently? Okay, good. So if I go back and look at this problem one more time, if I Now select to remove an H from the carbon that had a total of 2 hydrogens, right? I would generate this alkene. And if I look at it closely, I would realize that this alkene is a di-substituted alkene. So now I have a choice between a mono-substituted or a di-substituted alkene, right? Which one is more stable? And hopefully you guys remember, the more carbon substituted at my double bond, the more stable I'm going to be. So mono means there's only one carbon attached to the double bond. So the rest of these are H's, right? And over here, there's 2 carbons with 2 H's across the double bond. So this di-substituted compound is the major compound because it's the most stable alkene. It's even in this trans orientation. And this is what this line was trying to help you guys see. That if I look at where the methyl groups are in relationship to this line of symmetry, you realize there's one on the right-hand side and another on the left-hand side. So because they're on opposite sides, they're trans to one another, right? We're gonna try to work on some more of these today and probably also on Friday, all right? So the main rule that I want you guys to get comfortable with is that not all hydrogens are identical. We did an example yesterday where it didn't matter which side you pull the H, but now we're realizing it does matter. All right, so let's try another example really quickly.
Dr. Cooper,
Go ahead.
does that happen in E2?
Oh, this happens both in E2 and E1. You have to make that selection.
Okay.
Good question. Good question. Happens in both. Okay, so let's minimize this so I can kind of see the arrows here. All right, and let's react to this compound. I'm gonna have lithium hydroxide again. I'm gonna do this in this in acetonitrile. I'm gonna put my okay, so let's take a look at this compound. I want that to go there. It's too late now. Okay. So first of all, can we determine the mechanism type here, right? I'm usually going to have to tell you if this is a nucleophile or a base. In this case here, I want this to be a base. All this probably right over the reaction arrow. How this compound is being used, all right? So this is a base. So when I use the word base, what am I trying to say? What class of reactions am I trying to say? You guys still with me?
E1 and E2.
Or yeah, I guess that's right. I'm trying to say eliminations, right? I'm trying to say that please prepare yourself to think about doing an elimination. All right, so I'm gonna put that indicator here. I'm gonna make sure everyone's comfortable with that. Every time you see the word base here, this has to indicate elimination, all right? So this test that you guys got coming up, there's gonna be 2 main classes of reactions, either a substitution, and to do a substitution, I need what?
SN1, SN2,
Well,
or substitution.
okay, yeah, those are 2 classes. To do a substitution, I need a nucleophile, right? To do an elimination, I need a what?
Base.
A base, right? That's the clue that you guys want to make sure you pick it up on, right? There's a difference between the 2. All right, so I think everyone is comfortable with the fact now that I'm definitely saying that this should be some class of elimination. Which elimination is this? Can you guys help me out really quickly? What type of aqua halide is this? All right, it's secondary, right? All right, I'm not gonna be able to get my full. Is everybody comfortable with that? Yes, no? All right, I hope so. Okay.
No, I'm not. Can you explain how?
Okay, so I have to look at the carbon that has the halide, right? So the key word here is alkyl halide. So this is the carbon that has the halide, right? And I need to look at that carbon and determine how many things are attached to it, right? So if I look at that carbon, I have one carbon here attached to it and that carbon there attached to it, right? That's all that's attached to that carbon, or two other carbons. So that makes this carbon secondary, right? Is everybody comfortable with that so far?
Yes.
Okay, good. So this is a secondary alkyl halide. Let's put that in gray. All right, what type of base do I have? Is this a strong base or a weak base?
Strong.
Yeah, this is strong, right? And the trick here, if you need to use it, please do, is whenever I see a metal, it's going to have to be strong, okay? Metals are indicating that there's probably a ionic bond, right? Lithium is going to give away its electron to become lithium plus, and O here, the oxygen, is going to gain an electron. It's going to have 6 dots or 3 pairs of lone, or 3 lone pairs, I'm sorry, with a formal negative charge, right? So that makes this compound ionic, right? All right, and my solvent down here, what type of solvent is this? Is this polar protic or polar aprotic?
Polar aprotic.
This is polar aprotic. The name of the solvent again is acetonitrile. All right, this is a polar aprotic solvent. All right. So which conditions are favoring right now? Am I favoring the the E1 or the E2 process?
The E2.
Yep. This is an E2 mechanism, right? And again, solvent typically dominates those type of chemistries, right? All right, we're going to do the mechanism here shortly. All right, let's see, can we do this without the mechanism? That's where I'm hoping you guys can get, but maybe not right now. All right, so the way that elimination works is that I need to pull, I'm going to put this question out here. I need to pull or remove, however you like to say it, I say pull, or remove a proton from a carbon neighboring the alkyl halide. I'm hoping everybody is with me so far. All right, this is what you need to mentally always think about when you guys are doing eliminations. All right, eliminations have to remove a proton to get to my product. All right. All right, so let's put this here. I'm going to try to put a background here because I want to make sure everybody is somewhat comfortable with that. Let's change that a little bit. All right, I need to pull or remove a proton from a carbon neighboring the alkyl halide. It's secondary, so I already know those 2 carbons, right? Those are the carbons in these boxes. Is everybody comfortable with that? These are the only carbons neighboring the carbon that has a halide, right here, right? Carbon that has a halide, where are my neighbors? Right here and right there, right? Is everybody comfortable with that so far?
Yes.
Okay. So let's look on the right-hand side. So the only thing is we need to count the number of hydrogens, right? So on the right-hand side, how many hydrogens are present here?
1.
Yep, there's only 1 H present on the right-hand side. I'm gonna bring that down, right? And this is why learning how to read line angle structures becomes very important, right? If you don't have that skill at this point, that's gonna make your life difficult, right? But again, to find out how many hydrogens are present, take a look at the carbon and do 4 minus the lines I see. So let me zoom in a little bit here. So for this carbon right here, right, I see 1 line here, 2 lines, and 3 lines. So 4 minus the 3 reveals that there's 1 hydrogen not drawn there. All right, over here for this carbon, how many hydrogens are present there?
2.
There's 2 hydrogens there, right? Very good. So Zeta's rule says what? I got to form the major product. That's always going to come from the more stable alkene. So my trick is what? Remove the proton from the carbon with the what? Fewest number of hydrogens. So which side do I form a double bond with to form my product here? Is it the right-hand side or the left-hand side?
Right.
That's right. So my answer is going to be, I'm going to lose my leaving group. I'm going to remove a proton, and I'm going to have a double bond there. Okay. Any questions so far? No questions so far? All right, let's do the mechanism of this right quick. I'm going to make this a little bit bigger. All right. This is the answer here. Let's go ahead and put this in red as well. All right, so let's work on the mechanism because you guys do need to know the mechanism here. All right, so the first step was actually, I'm sorry, this is E2, so this is all one step. All right, I need to draw the hydrogen that needs to be removed. So I'm going to go ahead and draw the hydrogen here. Okay. I'm going to take my base, which is OH minus. All right, I'm going to actually draw all the lone pairs this time. I haven't been doing that. And just want to remind you guys that for an oxygen to be a minus formal charge, it has to have 6 electrons or 3 lone pairs. It needs to also have that negative charge.
So would it still be right if we drew it like with the yield sign LiOH and then just draw the arrows coming from it, or we have to put OH minus?
Oh, you can put Li lithium hydroxide. That's fine. If you
Okay.
do that, you need to put a bond in between the lithium and the OH to show where those electrons at. Or you can do it like this and put a minus charge there. As long as if you have the charge, it's fine. If you keep it like that with no charges, make sure there's a line there. Because your arrows have to start at bonds or at lone pairs.
Okay.
That's something that I'm going to try to talk about tomorrow. But you guys know that electrons are, not tomorrow, I'm sorry, I said the wrong thing. But I'm going to talk about that on Friday. I just wanted to kind of cover some small things that I'm seeing that are kind of wrong with the mechanisms currently. All right. So in this case here, I'm going to go ahead and circle the electrons I'm going to use. So I'm going to go ahead and give that a red circle here. All right. So I'm going to grab this proton. All right, I'm going to make my own arrows today. It's probably not going to work. I'll try to make my own. Okay. So that's going to be our step 1. All right, and pulling, all right, this is going to take too much time. I just don't have enough time. I'll use the preset ones. All right, I'm going to pull that hydrogen here, right? The electrons in that bond are going to collapse to form a double bond, and I'm going to kick off chlorine here, right? Okay. So again, everything happens at one time. All right, and that's going to lead to my final product, which is here. Okay. All right, is there any questions with the mechanism here?
Are those double-headed arrows or just
These are all
single?
double-headed arrows. That's right.
Okay.
All right, so I'm saying 2 electrons here, so it has to be double-headed. There's 2 electrons in this bond. That's going to make a double bond here. There's 2 electrons in this bond that give a lone pair back. All right. For those that like to see this, you're going to lose lithium chloride here in that process. Okay. No questions, right?
Do we, on the test, do we have to include the lithium chloride, or we don't have to? You just do the mechanism?
Yeah, just do the mechanism. I'm more interested in the curved arrow mechanism, right? Can you show me how these arrows should work, right? Again, the base is going to grab a proton, right? So what's a proton? Just the hydrogen with no electrons. So what happens to the electrons that were being shared with hydrogen in a bond? Those 2 electrons are going to now make another bond between this carbon and that carbon, right? So this carbon would be over 4 bonds if it kept the chlorine, but conveniently, chlorine doesn't mind leaving with 2 electrons. So I'm saying that the 2 electrons that were shared between carbon and chlorine now go exclusively only to chlorine, right? So I'll get a chlorine minus now, I'll get the lithium plus, and there's also going to be, maybe I should draw this too then. Right. Also here is going to be some water, right? Because I gain an H on that oxygen that already had 1 H. Okay. Good. All right, so let's back up. Is everybody getting comfortable with these steps? All right, let's do another one of these. Let's do another one.
Before we move on, I have one question.
Yeah, go ahead. Yes,
What's
ma'am.
the E2 in that box? What's the E2? What's that stand for?
Yeah, this is a bimolecular elimination.
Okay.
There's 2 classes of eliminations, right? There's a E1 or the E2. All my conditions were favoring the E2 mechanism here. So this is why my arrows look like this. Everything in 1 step.
You said bimecular or dimecular.
Yeah,
Molecular.
bimolecular elimination.
Okay.
All right, let's work on our next compound here. I'm going to do this. All right, I'm going to take this compound and I'm going to have it stirred in just plain old water. Okay, I'm going to indicate here, I'm just going to copy it from the top, that I need this to act as a base. Okay. So I need to go ahead and draw my product if I can. Can you guys help me out for this one? So let's kind of work on, first of all, dealing with all my components here. What type of alkyl halide is this?
Primary.
Yep. This is primary alkyl halide. Is there any questions there? Good, no questions. What type of solvent do I have?
What? Weak.
All right, solvent is polar protic, right? And then what type of base do I have?
Weak.
This is a weak base.
So there's no. What is the solvent then? There's nothing under there.
Yep. This is a solvolysis reaction, right? This is where the solvent is the base and the solvent, right?
Okay.
Or the reagent over the arrow acts as both. How we call it? We talked about this. Okay, so this is a, I'll write it out here. This is a salicylic reaction, right? Right. And what does it mean to do salicylic? This is where the reagent over the arrow acts as both the base and your solvent. For substitution reactions, that reagent had to be the nucleophile and the solvent. But for eliminations, this needs to be both the base and the solvent. Okay? So what mechanism is this favoring? What will you guys tell me?
E1.
This is favoring the E1 mechanism. That's right. That's very important to recognize that, right? You have to recognize which mechanism you're using because it changes how the mechanism works, right? So what is the first step? What is the first step in an elimination process? Sorry, in the E1 elimination process. You guys hear me on team? I'm talking to myself.
The electron share between the carbon and the proton?
Not necessarily. No. Okay, if anything, the first step in every E1 or even an SN1 mechanism is the leaving group leaves. Right? And it's going to form a what intermediate when the leaving group leaves?
Carbon cation.
That's right. It's going to form a carbon cation. Right? So my leaving group is going to leave. And now I'm going to generate this compound here. I'm finally going to see my chemical symbol. This is not going to work. That. And this is called a what intermediate right here?
Carbon cation.
Yep, that's a carbon cation. All right. So what type of carbon cation is this? Can you guys tell me? If I had to classify it, what would we classify it as?
Primary.
Primary carbon cation. Very good. So what do we know about primary carbon cations? Are they stable?
No.
They're
No.
not. That's right, they're not. Typically, they don't even form. If they had the choice to, they wouldn't. All right. So why does this carbon cation form? Can anybody tell me? This carbon cation is okay to form because of the fact that there is a neighboring ring, right? There's even a hydride there as well, right? But the ring is what we want to focus on today. So the 3-member ring is extremely strained, right? So this is going to undergo what type of process next?
Ring something.
That's right. It's going to undergo a ring expansion, right? So I'm going to expand from a 3-member ring all the way to a what type of ring now?
2.
Out of 2, that's going, 2 carbons can't make a ring, but I'm going from a 3 to a 4-member ring, right? All right, and my plus is going to be on that carbon. Is everybody comfortable with that? Right.
I thought it loses a side.
Say that one more time.
I thought the ring loses a side.
No, it's called a ring expansion, right? So it actually needs to expand to a bigger ring.
So we didn't lose a side on any mechanism?
Say that one more time.
We didn't lose a side of a ring in any mechanism?
No, we shouldn't have.
Okay.
I don't think I made that error, but if I did, I mean, I'm prone to make mistakes. But I'm pretty sure I'm drawing all the rings getting larger here. Right? A 4-member ring is not all that good here, but it's better than the 3. So that's why this ring opens to relieve some of that ring strain. All right. So now I'm primary, but what is my classification once I do the ring extension? What am I now?
Secondary.
Yeah, I'm secondary. So is that productive? Yes, right? To go
Yes.
from primary to secondary, that's productive. All right. So now this is where you guys want to make that choice. All right. Typically, if this was a substitution, my nucleophile would come in and attack. But this is not that, right? Instead, this is an elimination. So what has to happen is that I have to look at the carbon neighboring my carbon cation now, right? I'm just adding some H's here.
Are you about to do a hydride shift or something? Or no?
No, ma'am. All right, I got to do this. The second step of an elimination, which is remove a proton. So this is why I'm drawing those H's. All right, so up top I have 2 hydrogens. On the bottom I have also 2 hydrogens. So did it matter which hydrogen I pull from?
No.
Doesn't matter in this case. Right, I should have made an example where it did matter. It's too late now. I'll generate another one shortly. Okay, so it doesn't really matter. It's not the same side. It's okay. Which side you go towards here, all right? But keep in mind, to form the major product, it would have mattered, right? I need to make sure that I always pull from the side that has the fewest number of hydrogens, right? So what is my base in this example? Water, right? So I'm going to draw water with its 2 lone pairs. Okay. And this is going to operate like a base. So I'm going to circle one of the lone pairs here. Right. And I'm going to have a reaction arrow, and this has to be a double-headed arrow here that's taking one of the hydrogens here, right? And this is going to cause the electrons in the bond to collapse to form a double bond. Right? So once I do this step, I'm going to form this compound here, and my byproducts are going to be bromide minus and just protonated water species. But again, this stuff right here is not that important. All right. So up top, my product should be this compound here, right? And this ring right here actually is fictitious. It'll be almost impossible to make this. There's too much ring string here, right? But for purposes, for us to kind of keep track of things, right? We want to make sure that we know that for E2 processes, all right, I'm sorry, for E1 processes, we need to show the Liebman group leaving to form a carbon cation. And if there's any potential rearrangement, we need to prepare for that rearrangement. And here we can make a 4-member ring, which is better than a 3-member ring, right? Then we can remove a hydrogen and collapse to form our double bond for our product. Okay, so good.
2 questions, Dr. Cooper.
Sure.
Okay, so how do you know where to put the carbon cation when you made a 4-member ring?
Okay, yeah.
Or does it matter?
In this case here, all these carbons look the same, but I can number it for you. I should have put a methyl on one of these carbons. Actually, I'm gonna do the same example with a different constituent, and let's see how that changes things. Give me 1 sec. I'll try to help you guys see that. All right, so carbon 1 is the carbon of that has the carbon cation. 2 is next door. 3 and 4 are as indicated here. Okay. What? It went right back in the ring. Sorry, give me 1 second here. All right. So the thing to keep in mind here on this ring expansion is that carbon 2 here initially has a bond with 3 and 4 and 1, right? But this arrow is saying here, break the bond between carbons 2 and 4 and give 4 a bond with 1. So that means that 2 is going to lose a bond. And when it loses 2 electrons, it's going to become a positive charge. So 2 is the carbon cation right here. 1 now gain a bond to 4. So 1 is going to be here. Now 4 is bonded to carbon 1. And 3 is just the carbon next to carbon 2.
Okay, my next question.
Yes,
So,
ma'am.
how did you know not to do a hydride shift? Because it would have went from primary to
Yep. So
tertiary.
that's right. When you see a string ring, that's going to dominate the chemistry, right? So it wants to relieve the ring strand over doing a hydride shift. But on a test and an exam, I won't set you up to where you have those 2 choices. There's going to only be one obvious choice. Right?
Okay.
So in a realistic case, this leads to a complex mixture if you had this compound. You would get some of the 4-member ring and you would get some of the product that came from the hydride shift, right? So you just won't get one product really from this case, you'll get multiple products. But I just wanted to focus on the ring expansion in this case here. That's the more common process just because that ring is so unfavored. But very good question. Very good question. You don't have to make that choice. There will be one clear choice on the test. Okay, I wanted to come back to this, right? So this is a good question. And I wanted to do this. What if I modify this, right? To where now there's no potential hydride shift. Okay. And we work out the major product here. Now what would the major product be? Okay. Let's take a look at the difference in our mechanism, all right? I'm gonna bring this down a little bit. All right, so again, the Liebman group is gonna leave, but I need to make sure there's a alpha group shown here. So now carbon 2 is gonna have a what attached to it? An alpha group, right? Does everybody kind of comfortable with that. I'm going to put a methyl group here as well on carbon 4. Is that yes or no?
Yes.
Okay, good.
Something like that.
All right. It's not that big of a difference. I just added a methyl group and I added an ethyl group here, right? So what I'm trying to prevent is that there's no hydride, right? Because next door to this carbon cation is just a carbon that has 4 bonds to attach, no H, right? So the only thing that could happen is to break open this ring. So now there's going to be some changes here, right? Carbon 1 will still have 2 hydrogens attached to it. Carbon 3 also. Carbon 4 is going to have actually, you know what? I want to move the methyl group to 3. I need to make this different. I apologize here. I'm trying to design a question where I can change this right here. Okay, that's what I want to do. So now if I look at this structure as drawn, I get a difference in the number of hydrogens neighboring the carbon cation, right? Carbon 3 has 1 H in the methyl group. Let's go ahead and write Me in here. And carbon 1 is going to have those 2 original hydrogens, right? There's 2 hydrogens here with a plus. Okay. So that means I have to choose the side that I pull from. And which side should I pull? You guys tell me.
Left side.
Exactly. I should pull a hydrogen from the side that has the fewest number of hydrogens, right? So in this case here, this arrow now should go here. And can anybody tell me why? What rule tells me to do that? What's the name of that rule that tells me to pull that hydrogen versus the other one? Nobody knows? This is Zeta's rule, right? What does Zeta's rule tells me? Let me get the spelling right of that. Zeta's rule says I need to form the major product, right? And how do I do that? I need to form the more stable alkene. So if I pull from the side that have the fewest number of hydrogens, that's going to help out. All right. So I'm going to pull this hydrogen because of Zeta's rule. And I need to show that the electrons in that bond between carbon and hydrogen are now going to form a double bond there. Circle that red. All right, so what is my product going to look like now? So it's going to change a little bit here. All right, so I'm going to have a double bond here with a methyl hanging off. I need to have my other stuff here on 2. This methyl group here. Right? So my final product for this compound or for this reaction is going to be this compound. And again, this is also the E1 process, right? So are we getting somewhat comfortable with this? Yes or no? All right, I guess so.
We're trying, bro.
Okay, okay. And it's a skill that comes with practice, right? I just got to get myself some practice problems. I got to go online, look in the book, and try to make sure I'm comfortable with that, right? But if you can start to see these mechanisms, if it's an E1 process, remove the leaving group or the halide, generate that carbon cation. If it rearranges, go ahead and rearrange it. And then from there, try to determine what's possible, right? If I can remove a hydrogen from a neighboring carbon, right? The carbon that has the fewest is going to be the one that leads to the zeta product. Right? We'll decide with the fewest number of hydrogens.
Science is back.
All right, so I'm going to end class with these two notes, and then we got to pick this up soon. Next class is that what if I want to pull, or I'll say remove a proton from the side with the most hydrogens, right? Is that possible? And you guys can learn that this is possible. This is called the Hoffman or Hoffman elimination. And to do this, I need a bulky, I'll say the word big here, big, bulky base. Okay. We'll talk about those bases next class. If you use a big, bulky base, you're going to pull from the side that has the most hydrogens, right? So that leads to a different product. All right. The last thing that we need to talk about are stereochemistry requirements. All right. So what does that mean? All right. For the E2 process to even work, if there's stereochemistry, we need a anti-perplanar relationship between hydrogen, right, that's the wrong word, sorry, the proton removed and leaving group, which is usually the halide, okay? So that means that they need to be, in other words, you can say trans to each other. So if I have an H on a wedge, my leaving group has to be on a dash, and vice versa. If I have an H that's on a dash, my leaving group needs to be on a wedge. If they are cis to each other, if the H that I need to remove and the halide are on the same face, they will not do an E2 process. Okay? All the cases so far, that has not been a case because I haven't drawn any stereochemistry yet. Right? These are all the single bonds. Right? Or up top here, I didn't draw any stereochemistry near door. There's stereochemistry here, but I didn't draw anything else here. Right? So we're going to start to see what happens when I start to draw stereochemistry around for those hydrogens. Right? And there's two kind of new reactions that come up, something called a dehydration and something called a Hoffman eliminations for amines. Two little simple reactions, and we are done with material. All right, so my goal here is to try to get this in a PowerPoint slide that I can release to you guys before class on Friday so that you can look over this so it doesn't feel like you're learning this for the first time there. But it should be straightforward, I believe, all right? We should be able to use the bulky base correctly to pull from the opposite side, all right? There's probably going to be only one question on the test. There'll probably also be only one question on the test where you make sure that you're pulling the correct hydrogen with stereochemical relationships. All right, for E1, it doesn't matter because E1 goes to a carbon cation, so that all that stereochemistry is lost once you leave that leaving group. Once the leaving group can fall off, there's no more stereochemistry to be concerned with. But for E2, I do have to pull the correct stereochemical relationship between the hydrogen and the leaving group. Okay. Actually, these last two I'm going to show, they won't be on the test though. I just want to cover this. These will come up again a little bit later in second semester. But I'll just talk about those because they are in the family of E2 and E1 reactions. All right. Any questions so far for anyone? I'm going to stop the recording so that you guys can ask away. Okay.